Welcome, Hornets. We're going to be taking a look at limits at infinity today. Specifically, how do we take a look at limits at infinity when we have rational functions? Now, normally, when we have just a normal function and we're working with finding a limit at infinity, let's just take a peek. It's fairly straightforward. All we do is ask ourselves, is this growing or decreasing? If the function is growing as the values of x get larger, then we know we're heading toward positive infinity. If, however, we are plugging in our values and we end up getting negative numbers, such as negative 3x squared plus 1, this now grows infinitely toward the negative. I recommend people simply make a table of values to try to find them. But when we're dealing with rational functions, we can't just do that. We have to think a little bit more carefully about what we have. So what we do is we start off by taking a look at what is the situation. If f of x is a specific composite function, which has a function on top and a function on the bottom. And we're looking at three situations. The highest power is contained in the denominator. Now, when this occurs, the limit will always be 0. Let's take an example. The limit as x approaches infinity for 5x over 7x squared plus 1. Now, in this situation, what we're looking at is a situation where the higher power is in the denominator. Our rule tells us that this limit must be 0. But the reason why involves calculus and the specific rule that says when we have a power of x in the denominator, and that power of x in the denominator is greater than 1, and our numerator is some integer, then this will always give me a 0 for the limit as x approaches infinity for this function. Notice, this is what we're talking about. We're given this wonderful function, b over x to the some power, and if b is an element of the integer set, and a is some value greater than or equal to 1, then we know that this rule is true. Now this is important to us. Oops, I kind of cut that off. Let me rewrite that again real quickly. So in this problem, what we would be doing is we would be multiplying by an equivalent form of 1. That equivalent form of 1 is going to be the highest power in the problem. In this case, x squared. Notice that when I distribute, I end up getting the limit as x approaches infinity for 5 over x when I simplify, divided by 7 plus 1 over x squared. Since 5 over x fits this pattern, we know that we're going to get a 0, and the denominator has a 0 as well. But when we simplify it, our answer simply turns out to be 0. So here's our first situation, when the highest power is contained in the denominator. Our second possibility that we might encounter is that the powers are equal. So if we suddenly have a situation where the highest power in the numerator is equal to the highest power in the denominator. Then the limit is the ratio of leading coefficients. So let's take a look. If I have the limit as x approaches infinity for 3x squared plus 2x minus 5 over 7x squared minus 4x plus 2, we are going to multiply by the highest power. 1 over x squared, 1 over x squared. We're going to distribute it just like we did before. We're going to simplify it as we do. The limit as x approaches infinity is equal to 3 plus 2 over x minus 5 over x squared divided by 7 minus 4 over x plus 2 over x squared. Notice how this simplifies. This will simplify into 3 over 7. The other pieces are simply a plus 0, minus 0, minus 0, plus 0. And our result is 3 over 7. Here's our second situation. The third, it's not a very pleasant one. And it's one that we're going to be doing in a similar way. So don't worry about graphing this. Just recognize that things are happening here. This is when the highest power is in the numerator. When the highest power in the numerator we have a slant limit. That means that our limit is going to be positive or negative infinity, and we just have to figure out which is it. Let's take a look at an example. The limit as x approaches infinity, and we're going to put negative 7x to the third plus 2x squared minus 5 divided by 2x plus 1. Now, when we're doing this, we want to do a little bit of a mimic of long division. Now, if you recall, long division requires us to take the divisor and divide it, or the first term in the divisor, and divide it into the first term in the dividend. The dividend is the top, the divisor is the bottom. And we would end up with negative 7 halves when we did that. And that would give us an x squared. But what we're going to do is only part of it. We're going to multiply by 1 over x because that's the highest power in the denominator. We're going to distribute again and simplify and see what happens. Notice we get the limit as x approaches infinity for negative 7 over x. Let's just simplify it as we go, Mr. Lamb. So we're going to have negative 7x squared plus 2x minus 5 over x divided by 2 plus 1 over x. Now, according to that rule that we've already discussed, we know that this is going to be a 0, this is going to be a 0. We're really looking at the limit as x approaches infinity for negative 7x squared plus 2x. Now we can go back to our original of finding limits by simply plugging in the infinity and asking, is this going up or is this going down? And we can clearly see that that negative 7 multiplied by the infinity squared overwhelms the 2 times infinity, and our answer grows infinitely small, giving us a negative infinity as our answer. So these are the 3 situations you have to watch out for when you are working for limits at infinity. Let's just go over them again real quickly, please. If we have a polynomial written f of x as a top and a bottom polynomial. If the highest power is going to be of the g of x, and it's equal to the highest power of h of x, then the limit is the ratio of leading coefficients. If the highest power of g of x is less than the highest power of h of x, the limit is 0. And if the highest power of g of x is greater than the highest power of h of x, the limit is a slant limit and equal to the quotient. And to find our limit, we're going to be either checking to see if we go to positive or negative infinity. Thank you very much, Hornets. Have a good night.